Okay. Let us understand the modes of heat transfer first of all. Conduction, convection, and radiation. There are three modes of heat transfer.
Okay.
These modes of heat transfers are in detail explained or understood by some scientists. Like conduction is understood by Fourier, then convection by Newton.
Okay.
And this one by Stephen Boltzmann.
Yeah.
Okay. They have given us the laws for these modes of heat transfer. Fourier has given us law of conductivity, that is Q is equal to minus Ka dt by dx.
Yes.
You understand all the terms in this formula?
Yes, more or less. Area and change in temperature, right?
Yes. You can say this is area of cross section through which the heat flows. Like you can say if this is a slab.
Yeah.
Then in this formula, this A is basically if heat is flowing from this area to this area, like this cross section to the next cross section, then it can be rectangular, it can be spherical, it can be cylindrical, any kind of shape that would represent the area. dt by dx is basically rate of change of temperature with thickness. What does it mean? It means that this is the
direction of heat flow, right?
You can say direction, or this is the length of the substance through which the heat is flowing.
Okay.
It flows because of temperature difference. That is the only sole reason behind heat transfer. If there is no heat transfer, there won't be. So if there is no temperature difference, there won't be heat transfer.
Heat transfer. Yeah.
So more the heat transfer, more the temperature difference, more the heat transfer, and it always goes towards the lower temperature. The heat always flows towards the lower temperature. So suppose this is one surface. This is at some temperature T1, and this is at temperature T2, wherein T1 is more than T2. Then it will create a situation automatically wherein the heat will flow from higher temperature to lower temperature. There are some basics of this heat transfer, like why exactly it flows. It flows because of the potential difference, because the energy flow is always towards the lower potential.
Okay.
You understand these terms?
Potential difference. Yes, I think so.
Okay. See, there are many kinds of students. Like there can be some student who doesn't understand even the word potential. There can be someone who understands all these terminologies. So the more I understand what you know, it will get easier for me to explain.
Yes.
Okay.
Okay. I'm very weak at it. I'll just let you know earlier.
Be very frank. Okay. At any instant, if you feel like there is even 1% of data which is not getting absorbed in your
yes, I'll ask.
Okay. Because I've been doing this for years. This is what I teach to the crowd of 100 and 200.
Oh, okay. The thing is, okay, this course has been like, I just started it. It's only been a few weeks. So they're actually covering it very quickly.
Normally is what these college teachers do. They are like, they assume students know all the basics.
Yeah.
And they go really fast.
Yes.
And at any instant, if you feel that I'm going fast, just let me know.
Okay, no worries. So far, so good.
Okay. See, you should understand that heat transfer. Do you understand the terminology steady flow? Steady flow.
I think so. No, I can't remember.
Like even if you simply translate the meaning of steady flow, what do you understand?
It just flows steadily, constant.
No? Okay. Now, when it comes to science and engineering, when you say constant, that means some parameters should be constant. So
at the same rate.
What?
At the same rate?
Yes, you can say that. The rate comes with the function of time.
Yeah.
Right. Okay. So you can say when they say steady flow, it means at every instant the flow rate is same. It means you cannot relate this example in our day-to-day life.
Okay.
Like you are having a beverage which is hot beverage.
Yeah.
At a very next instant it will get colder because it will lose out heat and the temperature will drop.
Yes.
That is not an example of steady flow.
Okay.
The steady flow example would be like you've got an electric geyser, you have switched it on.
Okay.
And at every instant some power is getting converted into heat.
Yeah. And the same amount of power, is it?
Yes. So that switch, until unless that switch is kept on, and that heat is utilized somewhere to heat some fluid,
Okay.
that state is steady flow.
Okay.
So you will never have steady flow around you. It is completely an engineering application, wherein sometimes you switch on the application or the object or machine and it runs for an hour. In that case, you can expect steady flow.
Okay.
Okay, so these examples don't actually, you can find in our day-to-day life. So sometimes it becomes really difficult for students who are understanding or trying to correlate with the topic.
Okay.
So basically, whatever you will be studying will be of two types. Either it will be steady flow or it will be a non-steady flow.
Okay.
When it is a non-steady flow, such topics are called as transient heat transfer.
Okay.
Transient, it means in between. It is in between change, transition. Basically, it is derived from our transition.
Transition. Okay.
Okay. So either
this is for like the laminar, turbulent, and transient.
Those are types of flow. Okay. Those are types of flow of fluid.
Okay.
It's part of your chapter convection.
Okay.
Okay. So first of all, we need to understand heat flow. When it comes to heat flow, not necessarily every time there will be a fluid flow.
Ah, okay.
Fluid flow will come only in the chapter of convection.
Convection. Okay.
Otherwise, there won't be any kind of fluid flow like when it comes to conduction or radiation.
Okay.
Okay. So in this entire subject, there will be heat which will be flowing. It will be a function of time. By default, unit of heat is joules.
Okay.
Because it is flowing, so it becomes function of time.
Okay.
Right? Some kilojoule is going at the beginning of time, and you have lost some amount of heat at the end of time. So that becomes function of time.
Okay.
So that is like joules per unit time. And that is where the unit of heat transfer becomes watt.
Okay.
Okay. So there will be two types of heat transfer topic in your subject. That is, one is steady flow. And secondly, I think you talked about Biot number chapter. Do you remember that transition flow or lumped heat system? Is there any such topic?
Again, what is the other one?
Lumped heat transfer or transient heat transfer. Do you have any such topic in your syllabus?
I don't think so. I didn't get those.
Okay. Can you read out the subject conduction?
Under conduction, huh?
Subtopics of conduction.
Subtopics of conduction.
Okay. You can just do one thing. Just take a snap of your syllabus copy and WhatsApp me.
Okay, but the thing is, it's not very clear. Okay, I'll just send it to you.
It is very difficult to understand those terminologies for students. So just
I was thinking I can send you the slides, maybe.
No, not an issue. Send me a slide, whatever you can.
Okay, I'm just going to send you this.
Or if you have it in your desktop, you can share your screen.
Okay. They didn't really do much on conduction, I think.
Okay, the week one is introduction, thermal fluids, heat transfer mode, then thermal resistance, shape factor, critical radius insulation. Okay.
Let me just.
Fluid dynamics and convection heat transfer flow, external forced convection, flat plate and cylinders.
This is the one I have.
So is it the lecture which your professor have taken?
Sorry again?
What are these slides? Like, is it the lecture that your teacher has taken?
Yes, this is from the lecture. I mean, as in, he went through this for conduction.
Okay. Thermal resistance concept, series parallel. Okay, these are also like very basics. Then, do you understand all this parallel and series concept?
Yeah, the resistance, right?
Yes.
Yeah, I do.
One-dimensional conduction equation, three-dimensional conduction equation, heat generation. Yes. This topic, heat generation.
Mm-hmm.
this is the topic of transient heat transfer. Okay.
Oh,
Like,
okay.
when there is heat generation, there comes a function of time where it changes with time.
Oh, okay. Heat generation.
Thermal boundary condition, heat flux boundary condition, insulated boundary. So is it a lecture of entire week, or they have covered it in a single lecture?
In a single lecture. Is it? Yes.
It's a single lecture.
It's a single lecture.
And what do they
Yes, that's how fast they went. So everyone
really expect that students will absorb all the content in a single lecture?
Yes.
Okay.
So yeah. This is a single lecture. And then the next one we moved on like the next week.
Okay. That is really tough to absorb for student level, I can understand.
Yes.
Where are you from?
Singapore.
You're from Singapore only?
Yes.
Okay, okay. Okay, we'll go through the topics one by one, no issue.
Okay. Can I just so those that I sent you were the topics that need to be covered for the exam.
This slide you're talking about?
No, not the slide. Let me see. The one before the slides, I sent you pictures. Oh, I haven't? Okay, I think I haven't. Let me just send it to you.
When do you have your exam?
August 13.
August 30th.
13.
13. Okay. Internal pipes.
These.
You had a subject called as fluid mechanics in your second year?
Okay, so the thing is, okay, I did my diploma like many years ago, so I can't recall much of it. And then I decided to take this degree and they allowed me to enter the third year.
So it is like directly into third year?
Yes.
Oh. Okay, so
So
basically,
we did like a bridging course, but it doesn't cover much exactly. We did some fluid mechanics and all, but not so intense, I guess.
because the topic like internal pipes, it has the definition of laminar and turbulent flow. These are all from fluid mechanics.
Yeah, but I do understand when they talk about it sometimes. So.
Okay, yeah, velocity profile, then entrance region, hydrodynamic length, mean temperature, thermal entry length. Okay, Nusselt number. Understand the difference in the following equations. Solve the problem dealing with constant surface heat flux, and then solve the problem dealing with constant surface temperature. Okay. These are the topics that we cover in convection chapter basically.
Okay.
Okay, we can understand these topics. Then there is natural convection. Okay, internal pipes, over here it is called as forced convection. And secondly, what you have shared is natural convection. Then radiation concept. So these three images which you have sent will come in your exam.
Yes.
Okay. Do they give you some numericals to solve, or you'll have to just go through some reference books?
No, I think it will all be in the question. Like the questions I sent you.
These are the only questions?
No, I mean like similar to that.
Similar to them. Then where can you practice other numericals? Like where will you get them?
Yeah, they don't give any resources like that.
You don't have any
tutorials, I think. There are some tutorials. I can send some tutorials.
Okay, and what book are you referring?
Oh, no book.
No book.
Yeah,
Okay.
they just like have tutorial questions and stuff.
Okay, I have a PDF of a book. I'll share it with you. Don't worry.
Okay.
Okay, it's like entire book of heat transfer. It will have all the topics. It is by an Indian author, but
Okay.
it will help you out.
Okay.
There will be some solved.
Do you understand?
Okay.
Is it easy to understand?
Very easy. Like,
okay.
I hope you understand. Indians are okay at English, and they make sure that the language is very simple. Because majority of the people who do engineering are not that fluent in English, so even they should understand what exactly they're talking about. So make sure it is very easy. At least language. Okay.
So I'm just going to send you whatever tutorial I have that they've gone through.
thermal resistance approach. These are series parallel numericals.
Mhm.
Okay. Numericals are easy, no issues.
Okay. So
Okay, let's see if you can solve some conduction and conduction numericals. Okay, as per your tutorials, and we will go with it.
I don't think I can. I really
Are you
don't think
allowed
I
to
can.
use scientific calculator in your exam?
Yeah, we can use scientific calculator.
Okay. Tutorial 2, 3, 4. I think I have not received your first tutorial.
Oh, there wasn't a one. If someone
Okay,
just didn't have that.
there wasn't one.
There isn't one.
Okay.
It only starts from 2, so
Okay, maybe they must have introduced this subject in your first lecture. In tutorial 1.
yeah, maybe.
Okay. Okay, no issues. Let's start then. We will go with the flow and let's see. And the moment we feel we can solve the numericals of each tutorial,
Okay.
with an instant the basics are clear, we can go with them. Okay.
Okay.
So we were at the flow. I hope you understood about the types of flow: steady flow and transient flow.
And
A flow
transient
is
flow, yes.
steady when things don't change with time. When heat transfer
Okay.
don't change with time.
Okay.
Like a body is rejecting 2 watt of heat every instant. Such
Okay.
example would be for steady flow.
Okay.
But if an example is given such as a hot egg or a bowl of soup or a mug of coffee is kept in a room,
Mhm.
it will lose heat and eventually with time the temperature will drop.
Correct.
Such example is transient heat flow.
Okay.
Okay.
So in this steady flow, what is the example again?
Steady flow would be when the heat flows and the temperature doesn't change.
Any example?
Tube light in your room, a bulb in your room.
Okay.
When you can say not at the beginning of the rays coming out of the bulb, but at later stage,
Mhm.
when the equilibrium is built, you can say the highest temperature is reached.
Okay.
After that, the amount of heat rejecting or coming out of the bulb will be same until and unless you switch off the bulb.
Oh, okay.
Right?
Understand. Yeah. So non-steady flow will be heat transfer changing with time.
You can say that.
So
Unsteady.
if I leave a bowl of soup, the temperature drops, is it?
Yes, that is non-steady flow.
So that is heat transfer changing, the temperature dropping?
Yes, it is changing. Initially, when it will be very hot, the heat transfer will be more.
Ah, yes. Okay, I get it.
Okay.
So because the temperature becomes a bit colder, there's lesser temperature difference.
Oh, yes, true. When the temperature difference is max, the heat transfer rate is max because Q is proportional to delta T.
Okay.
Perfect. So eventually heat transfer rate drops. That
Okay.
is unsteady flow.
Mm.
Okay, this formula is simplified for applications like a slab or something which is a brick which has got a uniform cross section, wherein the cross section doesn't change with time. Like this slab, it has got cross section at the entry also same and at the exit also same. Or you can take a cylinder wherein when this end is made kept hotter and this end is kept colder, heat will flow from hotter end to colder end.
Okay.
When the heat will flow, the cross section will remain same throughout, right?
Yes.
When the cross section doesn't change, such topics are referred as slab, wherein this formula can be directly used. Q is equal to minus Ka delta T upon X, where K is the thermal conductivity, which is the integral property of a material. Every different material will have its own K.
Okay.
It's like if it's a good conductor, it will have a good K. If it's a bad conductor, it will have lesser K.
Okay.
Okay. So K is like integral property. It is something which the object is born with. You can say that. Okay. A is the area of cross section. Delta T is the temperature difference from one end to another end. And K is the length of the slab. You can see over here, the K is kept constant. In some cases, K is not constant. K is function of the length. I hope you don't have such topics in your syllabus, because mostly such topics are for postgraduates.
No, I don't think we do.
Mostly the subject is called as isotropic. Isotropic is basically a material which has got a uniform or homogeneous K. Okay, let us assume you have homogeneous K, because I saw the numericals, they don't have any such equations. What they have given is directly K.
Yeah.
Okay, so when K is simply a constant value, the heat transfer from one end to another end, if the temperature difference doesn't change, will be constant. And if I draw a graph of that slab or a cylinder, you can see the temperature linearly dropping. You can see the temperature linearly dropping. It is like a linear function. It means you understand the word linear, quadratic, cubic?
I do. Yeah.
So if it is linearly changing, it means you don't have to solve again the heat transfer question to find a temperature at any point. You can simply apply linear interpolation, like mathematical difference.
Okay.
And you can find the temperature at any point.
Okay.
Okay, like suppose they have asked us what is the temperature at the midpoint. And suppose over here the temperature was some 40 degrees Celsius. Over here temperature was some 20 degrees Celsius. You can directly say here the temperature would be 30 degrees Celsius.
Okay, get it.
That's why it is a linear function.
Okay.
Had it been a quadratic function or cubic function, it would have been difficult for us to find the temperature directly.
Okay.
In that case, the K becomes function of the length. Okay. Is it okay if I take a call?
Yeah.
Hello. Nine. Yes. ऑनलाईन लेक्चर आहे, मी सांगितलं तुम्हाला. माझं दुसरं ऑनलाईन लेक्चर चालू आहे, म्हणून मी भेटू नाही शकत असं म्हटलं. हा, उद्या भेटा. मला कॉल करा ना सकाळी तुम्ही एकदा. हो चालेल. हो. Okay. Sorry, let us get back.
Okay.
So we were about the heat transfer equation. Sometimes there can be question wherein they are asking you temperature at some other point. Right?
Okay.
In this case, you can simply apply linear interpolation. Do you understand how to apply linear interpolation? Do you know the mathematics?
Minus 20 divided by 2 and then add it to 40.
Okay, like if suppose I need to find temperature over here.
35.
You can say that, but what if it is not exactly in between? What if it is over here? What if it is over here?
I don't know.
Okay, you are smart. Okay, but try to understand here. You can apply maths. It is very simple. You can make it function of, you can make the temperature function of length. Like this is x equal to something. You can say 0. Here it is x equal to L. Over here it will be some x equal to x1.
Yeah.
Okay. Temperature respectively, you can say over here temperature would be T0. Over here it will be some T1. Over here it will be some TL. The linear interpolation is basically ratio of slope. Slope is ratio of differences.
Yeah, gradient, is it?
What?
Is it the gradient of the slope?
Yes, you can say gradient is like a slope.
Okay.
So you can simply take a gradient. Like the formula is dt by dx, right?
Yeah.
So you can take a ratio of temperature difference wherein you can say like final temperature minus initial temperature, right?
Okay.
TL minus T0 upon final length minus initial length.
Okay.
Okay. Then this was ratio of the dt and dx, right? dt
Yes.
and dx. Secondly, again you can take dt and dx over here in the form of unknown. Like you wanted this temperature.
Oh, so I do 40 and 20, and then later I find 40 and the other one. The one that I'm not sure of. They
Okay.
equal each other.
Right.
And
No,
then you solve for the.
just try to understand what I'm saying. Okay, this is starting point, this is the end point, and
Okay.
I will just explain to you a simple linear interpolation irrespective of the subject. You can apply it anywhere. Okay, you should make a table. You should make a table of the unknown which you want. Okay, it is a very simple relation. Suppose I know one parameter completely, and one of the parameter like temperature is unknown. I know x starting, I know x end, and I know a position where I want to know the value of T.
Yeah.
Everything is known except this temperature, right?
Yeah, so I just shifted around to solve it, right?
You can simply take a ratio. The ratio would be,
Oh,
okay, the ratio can be made simply by writing them in a table. Like first you write the T1, then you write the T2. This is T1, this is T2, and this is T. This is T. Then over here it will be x1, here it will be x2, and this is some x.
okay.
T1 40, T2 20, x1 0, x2 L. Let us say x is some number. If this is like 4-meter pipe, this is 0 and x equal to 4. Over here, let us say it is 0.5 meter. Getting me?
Are you assuming?
Yes, I'm assuming. Just an example.
Oh, okay.
Because the numbers make it easier to imagine.
Okay.
So what you would do is, this is something you can apply anywhere, okay? Anywhere when one parameter is directly proportional to another.
Another, okay.
Okay, like it is a linear function. So you can simply apply a relation herein T2 minus T1 upon x2 minus x1 is equal to T2 minus T upon x2 minus x. You can also take T1 minus T upon x1 minus x over here. All up to you.
Okay.
It's your freedom. So anytime if you feel like you need to calculate a temperature at a point, okay, in a question, you can use this relation linearly. There is one of the way. When the material is same throughout, then comes then comes the topic of series and parallel.
Okay.
Okay, what is series? Series kind of numericals come wherein one slab is attached to another slab and the materials of both these slabs are different.
Correct.
So the K changes. The K for material 1 would be K1, whereas K for material 2 would be K2.
K2, yeah.
Right. So in that case, you apply series relation. Series relations are quite easy.
Yeah.
Like you can see
I
materials.
only understand the resistance.
Don't worry, I'll explain to you in the form of numerical. Okay.
Oh, no, I understand resistance. I'm okay with resistance.
I will try to.
Please go through. I will still want to, in case I missed something.
Okay. Have you gone through a shape other than slab? Like, if you understand the resistance formula for slab R was, what is the relation of R? You know the formula of R?
Yeah, L over KA.
L upon Ka. L over Ka.
Yeah.
So L is basically this length.
Mhm.
K is the conductivity. Let us say
Yeah.
this is L1, this is K1, this would be L2, and this would be K2. And A is the area of cross section.
Yeah.
Okay. So over here the temperature is T1. Over
Mhm.
here the temperature would be T2. T1, if over here I'm talking, it means the entire surface would be at T1.
Okay.
T2, if I'm saying at this point, it means this entire boundary will be at T2.
T2. Yeah.
And over here, this entire surface would be at T3.
Yeah.
And they are in ascending order. So T1 is highest and T3 is lowest. So heat would flow from highest to lowest, right?
Yes.
And the series relation was written as Q is equal to delta T upon
R. Resistance. Right?
summation R, we would write, okay?
Yeah.
Delta T upon summation R. You can simplify it in the form of T3 minus T1 upon R1 plus R2.
R2. Yeah.
Okay. This can also be written as T2 minus T1 upon R1.
Yeah.
This can also be written as T3 minus T2 upon R2.
R2. Yeah.
Okay. R is L by K, so it will be L1 by K1A. This is about slab.
Mhm.
Let us cover the parallel of this slab also, and then we will talk about some other shapes. If you have it
Okay.
in a syllabus, we will cover that. Okay.
Okay, sure.
This is series, and parallel arrangement would be like two slabs of different K. Let us say this is K1, this is K2, having same length, L.
Okay.
They must have same length. Okay. If they don't have same length, then you will have to divide the material into different geometry.
Yeah.
Okay. So K1, K2, L. Let us say the area of this material is A1, area of this is A2.
Mhm.
It is very important in case of parallel that this entire surface is at same temperature. T1, this entire surface is at same temperature T2, right?
Yeah.
Okay. So what will happen is heat will flow from here to here. Okay. It will cover from the entire cross section at the entry to the entire cross section at the exit.
Mhm.
Okay. In this case, the you can say the analogical representation is given in the form of electrical circuit.
Yeah.
Right. So it is shown as if like this slab at the top is resistance 1. And
Okay, I just got a question about this. The one before this was in series, right? The vertical walls together.
right.
Okay. In this case, it is like parallel, right?
Yes.
Oh, so we're doing parallel now.
Yes. Okay.
Okay. I thought it was two series, so I got confused.
In this case, the resistances were in series.
Series. Okay.
Because this slab would represent resistance 1. This slab would represent resistance 2.
Yeah.
Here the temperature would be T1. Here the temperature would be T3. Here the temperature would be T2.
Yeah.
The heat entering would leave the object.
Yeah.
Okay. One very important terminology, or I hope this is something which students don't try to catch, that whatever is entering at every instant will also be leaving the slab.
Yeah. Same,
Okay.
right?
Yes, that is continuity.
Mhm.
Like the quantity of heat entering will always be equal to quantity of heat leaving. Only then the steady state can be achieved.
Okay.
Like if 10 kilojoule is entering
Mhm.
and 9 kilojoule is leaving, what does it mean?
Non-steady state.
Yeah. In that case, 1 kilojoule will every time get deposited or absorbed by this resistance,
Mhm.
which is impossible for any object to do it. Throughout
Okay.
its life, not that any object in the planet can absorb continuously heat. there
Okay.
will be a point wherein it will get saturated,
Yeah.
right? It is after the saturation that we study and solve the numerical.
Okay.
Okay, so that is where the steady state is reached. Okay, so heat is entering and heat is leaving, and the quantity remains same. That's why the formula comes that delta T for this, whereas delta T for this, or overall delta T can be simply written in the form of same Q.
Okay.
Okay, let us come down to this. Over here, the Q which is entering, you can say, and leaving the assembly, here it would be total Q, but partly it will get divided into this
And it'll come
and
together.
this, because not necessarily the total amount of Q will be same.
Yeah.
Because depending upon its conductivity, if it is a good conductor, more amount of heat will go. If it is a bad conductor, lesser amount of heat rate will flow over inside this, right?
Yeah.
So you can say the heat gets divided. Q1 heat enters, Q2 heat enters over here, and it is the total summation of this Q1 and Q2 will be equal to Q, which will be leaving.
Okay.
Temperature at this point will be T1, temperature at this point will be T2.
Yeah.
This temperature will be same for both. This temperature will be same for both. Only then it is treated like a parallel.
Okay.
Okay. So in case of parallel, same like electrical analogy, which we have studied in our basics in our childhood, it is written as Q is equal to delta T upon R equivalent. Over here we write the word R summation. Over here we write the nomenclature as R equivalent. Summation is basically addition of resistances.
Correct.
Whereas equivalent is basically an imaginary resistance which is replacing these two resistances.
Okay.
Such that the overall effect of this imaginary would be equal to the sum of or the total effect of both the resistances.
Okay.
Getting me?
Yeah.
Okay. So you can say over here the formula can be written as, again, delta T would be T1 minus T2. Okay. I think I missed the nomenclature over here. It should be written as higher temperature minus lower temperature everywhere. This should be written as T1 minus T2, then T2 minus, sorry, T1 minus T3, then T1 minus T2, then T2 minus T3. It should be always higher temperature minus lower temperature. Okay.
Oh.
Yeah. It should be always T max minus T minimum. Otherwise, the formula, the value might get negative. Okay.
Oh, okay.
Make sure that it is always higher temperature minus lower temperature.
Lower temperature. Okay.
Because in this diagram, we have written T1 as highest, so here it should be higher minus lower. Had it been like T1, T2, T3, then the formula was correct.
Okay.
Okay. Then here we can say the delta T. Here the delta T would be T1 minus T2 upon RE. Then RE is calculated as, do you remember the formula?
L over.
Okay, don't look at the formula, just see the screen. Okay, it is 1 upon RE.
Yeah.
1 upon R1 plus 1
Plus
upon
R2 plus.
Okay.
It goes on, yeah.
Whenever the resistances or whenever the slabs are in parallel, the equivalent resistance is calculated by taking the sum of the reciprocal of the resistances.
Yeah.
Okay. What normally people do mistakes in exam is they take the reciprocal and they simply equate it to RE. Make sure it is taken as reciprocal of the value. Okay.
Okay.
Because it is 1 upon RE, which is equal to 1 upon R1 plus 1 upon R2.
Yeah. So it's 1 upon all of them.
Sometimes what you might do, you know, 1 upon R1 plus 1 upon R2 you might end up taking it as RE. That will completely jeopardize your numerical. So do one thing, just take the summation and take the reciprocal. Okay. And then substitute.
So 1 out of the summation, right?
Okay. Or simply you can multiply it to this instead of dividing it to it.
Okay.
That is so fine. So that's how you calculate the parallel numerical.
Okay.
But you will not have such simple numericals in an exam. What you will have, or what I can see in your
It's a combination of series and parallel,
yes,
right?
it will be combination of series and parallel.
Yes. What do they mean by adiabatic?
Adiabatic, it means there is no exchange of heat from the surrounding. Means if I'm saying I'm in a room which is adiabatic, it means not a single amount of heat in this room will get lost in the atmosphere outside the room.
Oh, okay.
Okay. Whenever the word adiabatic is there, it means it is isolated from some other body or some other system or some other universe.
Okay, so the heat stays in there, it doesn't leave.
Adiabatic is also referred to an examples where there is no actual heat transfer.
Oh, okay.
Like some examples wherein there is mechanical work. So those examples are taken as adiabatic. Compression, expansion.
Oh, okay.
Okay, like you're compressing the air. In that case, the process is assumed to be adiabatic, and not a single amount of heat is lost from the system or absorbed into the system.
Okay. Okay.
Okay. So let us come to the combination. I think you have got some numericals of combination.
Yeah, I do.
In the tutorial 2, thermal resistance approach.
Okay.
Consider 1 meter deep and 3 meter high portion of wall which will act as a representative section of entire wall. What is it? Are they trying to explain the numerical?
Yeah, I think so.
Okay, they haven't given us the statement of the numerical. Right?
So I think the point forms are just information, and then the question is below probably.
Yeah, it is not a question.
Solution, I think.
They are trying to explain similar way what we are trying to do. Like they are trying to take some numbers and trying to solve the question or the application.
Okay.
So what exactly it is? It is like a hollow brick. It is like a hollow brick, and hollow brick has got some insulation in front of it, I think. Right? So R1, Ri. Okay, we haven't covered the convection chapter yet. Okay, so we will talk about that. Then we will get to the numerical. But before that, we will just see what exactly the diagram is.
Okay.
So it's an over here. There is an atmospheric interference, and then there is a brick.
That is R convection, right?
Pardon?
That is known as R convection. If I'm not mistaken.
There is no.
Okay, I'm just going to send you something that I have here that I went through.
Okay.
I think it's this. So is this the one?
Our convection. Yeah, that's what I said. We haven't covered the convection chapter yet.
Oh, okay. So we're just ignoring that first?
No. First of all, we are going to the diagram and then we will understand the convection. Okay.
Okay, no problem. Okay.
So far we have understood the series and parallel combination of conduction. I hope getting into numericals will be easier, right?
Okay, yeah.
Okay. So now let us get back to convection.
Okay.
The conduction equations are given by Fourier. Fourier formula in general is minus k dt by dx, and this formula can be directly used for cases where the cross section don't change.
Okay.
The form of q equal to delta t by r. Have you seen numericals like cylinder or hollow cylinder yet?
For conduction?
Yes.
There is conduction in cylinder.
Okay. So in that case, this formula cannot be directly used. Okay.
Oh, okay. For cylinder, you use R over R total. Oh, I got the same equation actually. How come?
Okay. No issue. I'll tell you. Don't worry.
Okay.
The in general formula looks same, but this R equal to L by K cannot be used. Okay.
Oh yeah, because of the radius, right?
Because of the change in area of cross section. Like you can imagine yourself. like if this is a slab,
Yeah.
this slab has got this cross section, and along the length you can see that area of cross section is not changing, it is constant.
Yes.
When area is constant, you can simply take R is equal to L by Ka.
Yes.
You can use this relation even for rods or a disc where heat is flowing from this cross section to this end. This area of cross section is not changing throughout the length.
Okay.
Only if the heat flow is axial, heat is flowing through the axis. But the moment heat flows in radial direction, the dynamics change. How? You can
So because your radius changes.
radius changes at every instant.
Yes. Okay. I get it.
Like at the beginning, the radius is smaller.
And then it gets bigger.
Yes, and it
Okay.
gets bigger. So that radius is square as a function of area.
Mhm.
So you can see area, the resistance is inversely proportional to area, and area has a terminology radius which is in the form of square of it, right? Because we know that area of cylinder or circle is pi r square.
Yes.
So it is like it is function of r square.
Yeah.
So that too in a reciprocal. And
Mhm.
because it is in reciprocal, once we integrate and we find the values, this formula of resistance for cylinders where the flow is radial is ln r2 by r1 upon 2 pi kl.
Oh, can I write this down? Sorry.
No, I will let you know. But have you seen this formula anywhere?
Yeah, I think so.
Okay, don't worry. Then I will give you in systematic manner. Don't worry.
Okay.
Okay. So let us get back to first convection. Okay.
Okay.
Because conduction part of slab is over. For slabs, another important heat transfer mode is convection. Convection relation is given by Newton's law of cooling. What he says is Q is equal to HA delta T. It means heat transfer due to convection is directly proportional to temperature difference and surface area in contact.
Okay.
Now this is not cross section. This is surface area in contact.
Okay.
Wherein in conduction it was cross section. Cross section means area perpendicular to heat flow.
Yes. Okay.
Whereas in this case it is surface area in contact with moving fluid or flowing fluid. Convection is something solely because of fluid flow.
Yeah.
When the fluid is flowing, it acts like a carrier of heat.
Okay.
It takes the heat from a surface and then give it to the surface at a lower temperature.
Okay.
That is convection. Right?
Yeah.
Okay. So over here, this H is coefficient of convection. It is okay. One more thing. Do you understand the units of K and H? Okay.
H is heat transfer coefficient, right?
H is heat transfer coefficient for convection.
Oh, okay.
K is heat transfer convection for conduction.
Okay.
It is also called as thermal conductivity.
Okay.
It is also called as coefficient of convection.
Oh, okay.
Okay. These terminologies you might mess up sometime.
Yes.
What actually will help you is the unit.
Okay.
For K, this M will not have power.
Okay.
For H, this M will have the power of 2.
Okay.
Like sometimes they will simply give you coefficient. And then you'll have to understand yourself what have they given us. Like, have they given us the value of K or they have given us the value of H? Are you getting me?
Yeah, I'm getting it.
Okay. Do you understand this terminology, Kelvin?
Oh, yeah.
Okay. In heat transfer, never ever try to convert Kelvin to degree or degree to Kelvin.
Oh, okay. You don't need to?
You don't need to. In other subjects like thermodynamics or refrigeration air conditioning, or where the temperatures have power, like in radiation chapter. In radiation chapter, you might have to take care of Kelvin, but otherwise never, or the simplest sentence would be, never try to convert this unit of H and K, no matter if it is in Kelvin or if it is in degree Celsius.
Okay.
Okay. Would you want to know the reason behind it?
Okay.
Okay. Simple. The K comes from Q equal to HA delta T.
Yeah.
The delta T is the difference of temperature.
Yes.
And no matter if the temperature is in Kelvin or if it is in degree Celsius, the difference will be always same.
Oh, it doesn't affect it. Okay.
Right? Because Kelvin and degree are function of an addition.
Yes.
Right? Because if temperature is given in degree Celsius, you simply add 273 and it becomes in Kelvin.
Correct.
If there are two temperatures in degree Celsius, or if there are two temperatures in Kelvin, the difference would be always same.
Yeah.
Right? So that's why if the K sometimes is given in watt per meter degree Celsius or watt per meter Kelvin, the unit need not to be changed, need not to be improvised.
This only applies for conduction and convection?
Yes, you can say that.
But radiation, sometimes you have to change something?
You don't have to play with the units if it is either given in degree Celsius or given in Kelvin.
Oh, okay.
It is applicable only to conduction and convection.
Okay.
For radiation, it is always in Kelvin.
Okay.
Okay, by default, in any thermal subject, the standard unit of temperature is Kelvin.
Okay.
But you will see majority of the times, even maybe in your numericals, it is given in watt per meter degree Celsius, watt per meter square degree Celsius.
So I just don't do anything with it.
You don't have to do anything. Just leave it as it is, because sometimes students end up adding the value of 273 nowhere at any point, and that will completely go wrong, right?
Yeah.
Okay. So that is very important. So the difference of unit, you must remember that K has the unit of watt per meter Kelvin, H has the unit of watt per meter degree Celsius, and it can also be written simply as watt per meter degree Celsius and watt per meter square degree Celsius. And you don't have to change or make any conversion. Okay?
Okay. Can.
Just take a call, okay?
Yeah.
Hello. आत्ताशी कॉल केला ना तुम्ही मला? हॅलो. हां. आपण मला आत्ताशी कॉल केला होता ना? मी आपल्याला बोललो ना की नाही, मी लेक्चर मध्ये आहे, मी नाही भेटू शकत. दोनदा सांगितलं तुम्हाला मी. हां. ओके. Sorry, these days examinations are going on, so there are many inquiries.
Oh, okay. No worries, it's okay.
What students expect is, like, if they have exam in next week, I should complete the syllabus within a week, which is not possible.
Oh, okay.
For them, I have my own application wherein all the recordings are there for the subject.
Okay.
All I do is just go through the recordings and you can ask the doubt. I cannot teach you the subject in entire week.
Yeah.
Okay, fine. Okay, when it comes to convection, convection is a surface phenomena.
Yeah.
And also is the radiation. Like convection and radiation always happens at the surface, whereas conduction is within the surface, within the cross section, right?
Okay, yes, yeah.
Okay. It is within the body. Okay. So whenever there will be a numerical, the convection will be at one of the end of the object. Like if this is a plate and it has got hotter surface at the bottom and colder surface at the top. If there is
a plate,
if suppose this is a plate, okay?
What plate?
Plate.
Like thick plate or flat plate?
thick plate,
Okay.
like a brick. Okay, you can say
Okay,
it's a,
okay, break. Okay.
okay. Sorry, suppose if it is a brick, it has
Uh-huh.
got some thickness x. Okay, and it has got some cross section area A.
Okay.
Higher temperature at the bottom is maintained,
Okay.
and colder temperature at the top is maintained
Mm-hmm.
somehow. So by conduction, heat will flow from hotter to colder,
Okay.
and beyond that, if there is some fluid, which
Okay.
is flowing. Okay, now fluids flow in two ways. One is in natural
Convection.
by density difference,
Okay.
and secondly by some external means. Do you understand both the?
By natural by density difference.
Do you understand the density difference heat flow?
No.
Okay, no issues. Suppose if this is a hot plate, okay, if this is a hot plate and there is some air around it, okay,
Okay.
there is some air around it, then by the exchange of energy, the air just touching the surface will get heated.
Oh, okay.
Okay, and you also understand that when the fluid gets heated, it expands.
What do you mean by that?
The volume increases.
Oh, it expands. Yeah. Okay. Yeah. Got
Okay.
it.
When the volume increases,
Yeah.
increases, the density decreases.
Ah, yes, I know that. Yes.
Okay. When the density
What do you
decreases,
mean by that? So it's like a convection.
okay, yes. So when the density decreases,
Yeah.
automatically the lesser dense fluid will go upward.
Up and the will go down. Yes.
And when something leaves the surface, there will be vacuum created over here. And
Okay.
that vacuum will pull the fluid around it, or it will pull the fluid in the surrounding which is at a colder temperature,
Yeah.
and ultimately the fluid flow will set. Ultimately, automatically, because of this density difference,
Mm-hmm.
the fluid will flow.
Okay.
If this fluid doesn't flow, there will not be convection.
Okay.
Okay, so fluid is flowing all because of its density difference. So there's a force called as buoyancy force, buoyancy or buoyancy.
Mhm.
What do you pronounce it?
Buoyancy.
Buoyancy, you have heard the word buoyancy?
Yeah.
What is buoyancy?
It like floats.
What?
Like it floats, right? Buoyancy.
Okay. Buoyancy is an upward thrust.
Okay. Yeah. The force. Yes.
Buoyancy is an upward force,
Yeah.
which is always in action and is always applied to a body which has got a different density.
Okay.
Like even you are sitting in atmosphere.
Yeah.
Because you are denser than air,
Okay.
you are not affected. Had you been lighter than air,
Okay. So there will be a
air
buoyancy force.
air would have pushed you up in the sky,
Oh, okay.
right?
Yeah. Like the helium balloon and all.
Oh yes, like if your body was made up of helium gas,
Mhm.
you would have gone up in the direction of, you can say, sky by buoyancy force.
Okay.
See, so that is the
Can I just check one more thing? Natural convection is by nature, is it? And then forced convection is like if you're on a fan or something, is it?
we are talking about the same.
Oh, okay.
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 So natural convection is because of buoyancy force.
Okay.
Nothing is by nature. Okay. Buoyancy force is basically an upward thrust which is applied to a lesser dense fluid or a fluid with lesser density.
Okay.
Because the air which was surrounding the plate got lighter,
Mm-hmm.
the heavier fluid pushed it in the upward direction.
Okay.
And that sets the current, that sets the flow. And this is called as a naturally generated flow because of density difference.
Okay.
Okay.
So what is forced convection?
In case of forced convection, suppose you are having your meal and that meal is hot. It gets automatically cold with time, right?
Yes.
And that is by natural convection because the air around it takes away the heat and it flies in the sky. Okay. But suppose if you don't have enough time, what you do, you will just take it and keep it in front of fan.
Yes.
Then fan or a blower will forcefully flow the fluid over the surface.
Yes.
When you will forcefully flow the fluid over the surface, it is like there will be every time new particle ready to absorb the heat.
Oh, okay.
Because ultimately fluid is the carrier of the heat.
Yes.
Initially it was going on its own, that was natural convection.
Yeah.
Wherein when you are using some fan or a blower, the velocity of flow is higher, and that is the reason why the body gets colder at faster rate.
So that is forced convection.
That is forced convection.
Okay.
If there is some mechanism used like fan, blower, pump, compressor, and
Yeah.
fluid flows because of that,
Okay.
then such convection is called as forced convection.
Okay. Okay.
Okay.
Yeah.
Okay. In both the cases, the only thing that differs is the value of H.
Okay.
The only thing that differs is value of H. Okay. You will have an entire big chapter to find the value of H. That is convection chapter.
Okay.
There are many numbers which you need to understand before that, like Nusselt number, Biot number, Grashof number, Rayleigh's number, Prandtl number, Reynolds number.
Yeah.
These are all the numbers you must understand before you're able to find the values of that H.
Okay.
But in this chapter, you don't need to find the value of H. They will directly give you the value of H, and you need to just solve the question by parallel and series method.
Okay.
That you need to do it in convection chapter.
Okay.
Okay. So the sole purpose of the convection chapter will be to find the value of H, understanding the geometry, understanding the flow.
Okay.
Okay. Are you still able to understand everything?
Yeah, I'm good. Yeah.
Okay. So I hope you understood convection. Convection, one is natural convection, another is forced convection. In natural convection, the flow either can be at the top of the surface, or maybe like this is a horizontal plate, or sometimes there can be a vertical body wherein the fluid is simply flowing along the surface, again vertically upward. In case of natural convection, flow will be always upward. Okay.
Okay.
Because it is by the density difference, so flow will be always upward.
Upward. Okay.
Okay. And in that case, you need to calculate this area in contact, and that is the surface area.
Okay.
Okay. This delta T would be temperature difference between the fluid and the surface.
Okay.
Okay. Like in conduction, it was the temperature difference between the end of the body. In case of convection, it will be temperature difference between the fluid and the surface.
Okay.
Like if heat is getting absorbed by the surface, then it will be this temperature minus this temperature. Like if the fluid is hotter and the surface is colder,
okay,
in that case it would be T1 minus T2. And if it's the other way around, like plate is hotter and the fluid is colder, it will be T2 minus T1.
Okay.
Okay. Just for simplicity, you can always make sure that the numbering is done in ascending manner, like descending manner. Like the hottest is given the number 1 and the coldest is given the number which is smaller, right?
Yeah.
So it will be like every time whenever you write delta T, it will be either T1 minus something, like T1 minus T2, T1 minus T3, or so on.
Yeah.
Okay. So now let us take the combined formula of conduction and convection. Okay. Suppose if this is a brick or a plate or a slab, if it has got some length L, this is the length of the plate, and it is square shaped, you can say. So it will be L by L.
Okay.
Let us say this is the thickness of plate. The bottom of the plate is at higher temperature T1. Then there is some fluid above the surface, which is at some temperature T3. And the top surface of the plate is at temperature T2.
Okay.
Okay. So the plate will have thermal conductivity K. The fluid will have thermal coefficient of convection H. So the electrical analogy over here would be it is like the slab and the fluid are in series, because heat would flow either in upward direction or in downward direction,
Okay.
always towards the lower temperature,
Okay.
because we assume that the hotter temperature is T1 and colder temperature is T3. The heat flow will be towards the colder temperature.
Okay.
Okay, this is just the way of representing the fluid. Okay.
Okay.
Never try to interpret with the actual fluid flow direction, because the fluid will be actually going in this way.
Okay.
This is just the kind of representation of fluid above the plate.
Okay.
Okay. So the electrical analogy of this diagram would be convection resistance, conduction resistance, temperature T1, temperature T2, temperature T3. The heat entering the conduction will be equal to heat leaving the convection. The resistance of conduction would be R conduction, and resistance of convection would be R convection.
Yeah.
Okay. And you can formulate it as Q can be written as hotter temperature minus colder temperature, T1 minus T2 upon R conduction, or you can write it as T1, no, sorry, T2 minus T3 upon R convection, or you can also write it as T1 minus T3 upon R conduction plus R convection. Easy?
Yeah.
Okay. Where R conduction is equal to L by Ka.
Yeah.
And R convection is equal to 1 upon Ha. It is basically this formula written as delta T upon 1 upon Ha is equal to delta T upon R, right?
Yeah.
They just have formulated this formula in electrical analogy. You understand the word electrical analogy, right?
Yeah, I do.
Why do they say electrical
Like
analogy?
the resistance to electricity, right?
Ohm's law, right?
Yeah.
In Ohm's law, we have studied I is equal to V by R.
Yes.
Over here, the current was flowing I, and V was the potential difference.
Yes. And
R was the resistance. In this case, heat is something which is flowing. The potential difference is the temperature difference. And the electrical resistance over there is replaced by the thermal resistance over here.
Okay.
Okay. So just for the sake of revision. So this is the conduction plus convection.
Yeah.
Now we will complicate the case and let us take conduction, convection. Okay. Conduction. Then let us take two slabs in parallel. And one fluid over here and one fluid over here. So we have kind of created our own numerical.
Yeah.
Okay. So maybe here is some hotter fluid which is trying to heat this surface. Let us say it has got some coefficient of convection H1.
Okay.
This is some layer of brick or insulation or any material. It has got thermal conductivity K1.
Okay.
This entire fluid will have some temperature T1. This surface will have some temperature T2. This entire surface will have some temperature T3. This entire surface will have some temperature T4. And again, there is a fluid at the end which has got temperature T5.
Okay.
It's like one hotter fluid is giving away heat to a colder fluid. Or you can say this is like your room. You're staying inside.
Yeah.
This is the air in your room.
Yeah.
This is the first layer of plaster. Okay. And then this part can be like, you can say a window, and this can be like your brick. You can say that.
Okay.
Or you can take it like a curtain over here. This.
Okay. Can I check something? From T3 to T4, it's still series?
Hold on. Okay. T3 to
T4.
No, it's parallel.
It has to be parallel because
is
they are okay.
So this entire surface, it has temperature T3. This entire surface is at temperature T4.
Mhm.
This was a single material, whereas these are two different materials of thermal conductivity K2 and K3.
Okay, Ken.
Okay, now we have kind of created a complicated numerical.
Mhm.
And this outside fluid will have coefficient of convection H2. Can you imagine this question now?
Yeah, Ken.
Okay, how to solve this now? Let us say
Well, what are we finding?
we are trying to formulate all the possible formulas.
Oh, okay.
Okay, suppose you need to find some temperature. Like suppose they are like give us this temperature T2 or T3 or T4.
Okay.
Okay, then what would be the procedure? How to solve it? So let us say this is the area of cross section A.
Okay.
Sorry, area of cross section A, and that will be also the area in contact with the fluid. So that will also be surface area.
Okay.
Like if this is a phone, if this is the cross section for heat flow, this will also be surface area in contact with the fluid.
Okay, Ken. Yeah, and yeah.
Okay. Let us say these two areas are A2 and A3. A2 and A3. Okay, this is A2 and this is A3.
They're different areas, is it?
Area A2 plus A3 will be A.
A, okay.
Right? You can see like this. This is A2 and this is A3.
Okay.
And this entire would be A.
Yeah, okay.
Okay. So let us say some heat or some heat not. If there is a temperature difference of T1 to T5, the heat will obviously flow from here to here.
Yes.
Okay. Let us give some thickness to them. Let us say this is having a thickness of X1 and this is having a thickness of X2.
Okay.
Okay. So you must draw the electrical analogy before you start with any numerical. Okay.
Yeah.
Before you start with any shape, any geometry, draw the electrical analogy. So what would be its electrical analogy? Its electrical analogy would be like, first of all, there is a resistance of convection.
Yeah.
Then there is a resistance of this layer of conduction.
Conduction.
They both are in series.
Yeah.
Right. So convection, conduction, right?
Yeah.
Let us name them as RA and RB. RA for this convection, RB for this conduction. Then these are two in parallel.
Yeah.
So you can just divide them simply into two resistances.
Yes. C and D.
Yes, you can say RC and RD. RC and RD.
And then R convection again.
Yes, there is again a convection, which will be RE, let us say.
Okay.
We can name some temperatures like T1, T2, T3, T4, and T5. Okay. Heat is entering over here and heat is leaving over here. And by default, it goes without saying that heat entering will be equal to heat leaving.
Okay.
So you can have many formulas over here. You can make so many formulas. Like you can have a basic formula. Q can be written as extreme temperature difference T1 minus T5 upon summation of all the R's.
Okay.
Okay. Now, what would be summation of R? Summation of R would be RA
Plus RB.
plus RB.
What plus 1 over RC plus 1 over RD?
No, that will make the equation wrong because you cannot simply put the reciprocals over here. Instead, I would recommend write R
separately.
equivalent.
Oh, okay. Yeah.
Just write R equivalent.
Okay.
And next comes your RE.
Mm-hmm.
Capital E. This is small, this is capital E. Okay. So 1, 2, and this is R equivalent for those two. And this is RE. How to find 1 upon RE? 1 upon RE will be 1 upon RC plus 1 upon RD.
Mm-hmm.
Right?
Yeah.
Okay. Now you can do mathematical relation and then substitute over here.
Okay.
But you should never write 1 upon RC plus 1 upon RD because that is the formula 1 upon RE and not of RE.
Okay, okay.
Okay. So that is how you can find 1 upon RE.
Okay.
And once you have 1 upon RE, you can take the reciprocal and substitute over here. Okay, now we will write the other formulas. Like, what are the other formulas? You can write, first of all, what is RA?
RA is convection.
Convection. So it will be 1 upon H1A, right?
Yeah.
Then RB,
RB will be L over KA.
okay, it will be X1.
So X1 over K and A.
K1A, but okay, K1. Okay. So RB, now what about RC?
RC will be conduction as well.
X2 upon
X2 upon K2.
A2.
I got a question. There's K2 and K3. What do I do? Oh, so I do it separately, is it?
Yes, yes.
Okay.
So RC will be for this and RD will be for this.
Okay.
So K2 for RC and K3 for RD.
Okay.
And not just K, even they also have different A's.
Yeah.
So RD will be
X2
yes.
over K3, A3.
Perfect. And RE?
RE will be 1
Oh yes.
over
1 upon
H2, A.
perfect. Okay. So these are all the resistances.
Yeah.
Okay. This we have written in the form of extreme temperature difference. You can also write them in the form of individual temperature difference.
Okay.
So this will be like Q can also be written as T1 minus T2 upon RA.
Yeah.
Can also be written as T2 minus T3 upon RB. Can also be written as T3 minus T4 upon RE. Can also be written as T4 minus T5 upon capital RE.
Yeah.
Okay. You can also have some combinations. Like you can have T3 minus T5 upon resistance addition.
Okay.
Now you can create many combinations, right?
Yeah.
Like just for an example, I'll give you one example. It can return a T1 minus T3 upon RA plus RB.
RB. Yeah.
Okay, that's it. So this is all about series and parallel when it comes to slabs. Do you have any question?
No, I'm good.
Okay. So this was something that the tutorial 2 was covering.
Mm-hmm.
There's a question, right? There's a question of bricks.
Yeah.
And bricks, plaster and foam.
Yeah.
Okay, will you be able to solve it?
I think so.
You want to try it?
Yeah, let me just find the question.
The tutorial solution week 2 minus 2.
Okay, consider 1 meter deeper. So it's question 2.2, right?
Yes. Okay, I'll do one thing. I'll just share the screen of my mobile. You can see that.
Yeah, okay, sure. Thanks.
Okay. Can I see the screen?
Yeah. Is it possible to zoom in?
Yeah. Hold on. Okay.
I just had the diagram. It's a little below.
Share it again. There's something wrong with it.
Okay.
I don't know what is wrong with the screen. It is not able
But
to.
it's okay. I got the question. It's fine.
Okay. Okay, we will just try to draw the question and see if you can solve it. Okay.
Yeah.
Have you solved it before? Did you try it?
No, it's my first time
Okay.
actually.
Fine. Then the question is like they have given us.
But they didn't give us the H value and stuff, right? Did they?
They must have shared the question somewhere else. This is like a solution of the question.
Yeah, that's the thing. I'm not sure where the paper is. I mean, that file is.
Okay. They have directly taken the values like H1 is taken as 10, K is taken as 0.026 watt.
Yeah.
Okay. Nevertheless, we can just simply understand the question.
Yeah.
Okay. How exactly would you solve this question? Just see. See, whatever solution they have given us, not necessarily you need to do the exact division of the areas. You can divide it in your own way also. So Abhi, now I don't know what exactly they have given in the form of geometry. Like, okay, they have given us. They have shown all the dimensions.
I've done it ready. Can I just show you what I have?
Okay, show me. Yeah, you have wrote the resistances, right?
Yeah. Is that correct? Oh.
Okay. We will just draw the diagram and see if the resistances are in the similar way or not. Okay.
Okay.
So the question,
Because we don't have the value of H and K.
they have actually given us the value in the form of solution itself.
Oh, okay. Let me just see.
If you go through the solution, you'll find all the values, K, H, everything.
Ah, okay.
Okay. They must have given you the question statement maybe in the classroom.
Oh, in the file, is it? I'll take a look later. I don't remember because I went through the video and I didn't see anything.
Most of
I'll
the
look through it.
do, yeah, they simply try to take such numericals to understand the topic. And they're like,
Oh.
let us say the K is something like this. Let us say the H is something like that. That's how they take an example so that you can simply understand the topic.
Okay.
Okay. So I hope you understand what exactly the practical application was, right? It was like a brick. It is a hollow brick, right? It's a hollow brick. It has got air in between. Or is there some material inside?
Air.
Air. So it's a hollow brick. Okay. So this is a brick and this is a plaster or a foam.
Okay.
No, sorry. So this is a brick and this is a plaster and this is a foam. Right? So this is the entire geometry. This is foam.
Yeah.
This is a plaster.
Plaster. Oh, and then there's a brick inside.
Yes. So it's like a normal construction that you see.
Yeah. Okay.
So it's a plaster.
So it's not convection, it's conduction still.
They have given us a convection over here.
Yeah, I mean for the brick and the Plaster.
They have given convection over here also and over here also. So there is connection
Okay.
to both the side. Okay.
Mhm.
Have you seen any construction site how exactly the bricks are in between the walls?
No.
Okay. So the example is basically when you start with a surface, like the process is, you put some amount of cement,
Okay.
okay, cement or a mixture of sand and cement.
Okay.
Over this, a brick is laid, and then some amount of mixture is again put in between for adhesion, and then
Okay.
again another brick is over here. So it's like there is a series of mixture of cement and sand,
And yeah.
and you can say plaster, and
Yeah.
then there are series of bricks, and again there is a mixture over here, and when you rotate this by 90 degrees, you can see this arrangement.
I see. Okay, I get it.
Okay, and above this, like in our house, what we see is it is all plain,
Okay.
and that is nothing but the layer of plaster and the foam.
Okay.
Okay, so that is what they are trying to illustrate. So
Okay.
over here we have got lots of material, like this is air,
Yeah.
this is air, and it will have some H. This is a foam, this will have some K.
Yeah.
Okay,
Yeah.
let's say this is K1.
Okay.
Then this plaster need to be divided. You need to divide this plaster.
Oh, why?
Okay, because you can see the geometry. It is not a single geometry for a flow of fluid. If the
Oh,
heat is flowing from here,
yeah.
you cannot distinguish if this is in series or parallel.
Mm-hmm.
To make it convenient for you, you'll have to
Yeah.
divide it either in this fashion. So this is like, this will be one layer, this will be one layer, and these two will be in parallel.
Oh,
Or you can do one thing, that you can simply divide it like this. All up to you. All up to you, the way you want.
okay.
What they have done is, I will have to understand.
So it doesn't matter how you divide it, as long as you get it right.
As far as your concepts are right, no issues. You will always go right.
Okay.
Okay. What we will do is, we will divide it vertically.
Okay.
Like I will draw a line from this end to this end, and then from this end to this end. Then it will be like air, foam, plaster, like 3 in series.
Yeah.
Okay, and after that, these are like 3 layers in parallel. This will be
Okay.
layer of plaster, this will be layer of brick, and this will be layer of plaster. They are in parallel.
Okay.
And then this will be like next series of plaster.
Mm-hmm.
Okay. If you assume it to be a single layer, for example, just for a time sake, you can
Okay.
say 1, 2, 3, 4, 5, 6, they all are in series.
Yes.
Okay, but you know that the one which you assume to be in series, it was nothing but 3 different layers in parallel.
Yeah.
Okay, so exactly this is how you have actually solved the question, or maybe the solution is given.
Okay.
So this is H1, coefficient of convection for the air. This
Mm-hmm.
is K1, thermal conductivity of the foam.
Yeah.
This is K2, thermal conductivity of plaster.
So,
This K2 will be applicable to every plaster material
okay.
because they are all same.
Can I check with you if I take, for the plaster here,
Okay.
I mean the first K2 and the last K2, can I just do the equation one time and just times 2 or something?
Go ahead.
You can do that, right? Okay.
Yes.
Just check.
No issues.
Okay. So
Okay.
then
I will just name it as K3. I will
yeah.
name it as H2. So now, no matter what the name is, you will never go wrong with the solution.
Okay.
Like over here, if you try to draw electrical analogy first, it will be exactly same what you have sent me. Like this is convection, this is conduction, conduction, three series, a parallel of conduction. Then this is conduction, this is convection. So if
Yes.
I draw convection, then conduction, three layers.
Yeah.
Three layers of conduction in parallel,
Mhm.
and then again conduction, and then again convection.
Okay.
This will have resistance H1 as resistance RA. Okay, here the resistance would be RA. I will use different color. Okay, this is RA. So here it will be RA. This will be RB. So over here it will be RB, RC, RC. These are three in parallel. So you can name them as RD, RE, RE. These two would be same. This part and this two part. The material is also same, thickness is also same, length is also. So you can simply name them as RD only.
Oh, okay.
This RC and this would be same. So you can name it as RC only.
Okay.
Okay. And now this will be your RF. So this is like RA, RB, RC in series.
Mhm.
Then RD, and then RE, and again RD. These two are like same, so it will be RC, and this will be RF. Okay.
Okay.
It is very important that you understand the area of cross sections at every instant. You can see that area of cross section and surface area for 1, 2, 3, 4, and 5 would be same. They all will have same area of cross section and area.
Okay.
But for these three areas would be different, because you should be able to imagine that you can see that area of cross section for all these three layers are same,
Yes.
right?
Yeah.
But
The other one is broken up, right?
yeah, so they are in three layers, like they are like sandwich. So it will have three layers. You need to calculate these areas separately for these three.
Okay.
In three-dimensional representation, it will look like this. And here I will name them as RD, RE, and RD.
Okay.
Areas would be different. Okay, but the area of the bottom part and the top part would be same by geometry, by symmetry.
Okay.
Okay, now do you have any doubt?
No.
Now maybe you will be able to solve this question.
Okay.
Don't you have like more questions on this so you can practice and make sure that you can't go wrong?
Yeah, that's the thing, they don't. That's the whole problem. They only have this. There's some in the slides,
Even the 2
but
point,
not many. I think like only 2.
like the tutorials which they have given is like, it is so incomplete. Even the 2.3 is like they haven't given you the diagram or something like that.
Yeah, I think I will have to go and find the tutorial. I'm not sure if there's a different one, but from what I know, this is what I have.
Okay. So these are like the simplest topic of heat transfer, what we have studied. This is
Okay.
like the basics of heat transfer from where things begin.
Okay.
Like if you do understand all these basics, the later part becomes difficult.
Okay.
Okay. So I would recommend just solve some numericals on this, go through them,
Okay.
and try to practice as much as possible. I have some book. I'll show you. Like if
Okay.
you
Are
want,
there tutorials there?
it's like complete book. You will find lots of content in it.
Okay.
Okay. Okay. See. Okay. Can you see this?
Yeah.
Okay. Just a minute.
Is there anything you want me to read up on before our next class or something?
No need to. Don't read. Like, my purpose to make you understand is like, if you don't understand basics, I will explain. Don't worry.
Okay.
But if you can read from your part anything, if you want to, just go ahead.
Okay.
Maybe because after reading you get lots of doubts. So once you have those doubts, it will get more interactive.
Okay.
Okay. See, this is one book. It is a huge big book. Okay. It is a book of 1,000 pages.
Okay.
So I will just go through the syllabus if possible. Okay. It is written by R.K. Rajput.
Okay.
Okay. The content goes like, they talk about the basic concepts with many numericals.
Okay.
We talk about thermodynamics first of all. You just have to go through the content in your syllabus.
Okay.
Okay. So this is something which we studied today, heat transfer by conduction. Then it talks about everything, critical thickness of insulation, that we will need to discuss. Apart from that, we have just covered the walls and slab kind of numericals. Yet we haven't discussed the cylinder and sphere type of numericals. In this case, even that they have explained, like conduction through hollow, sphere and composite cylinders.
Yeah.
It is very important to understand those. Then there is critical thickness of insulation and conduction with heat generation. Okay.
Okay.
Then there is this 2-dimension and 3-dimension that you have in your syllabus. After that, there is unsteady state, transient state heat transfer. Okay, then there is forced convection, which is the internal flow convection in your syllabus. There is free convection.
Is it possible to skip the conduction and head to the convection first?
We can do that, not an issue.
Would it affect, like, do I need to know something in conduction that will be leading to the convection?
No, there will be something more I'll have to teach actually, nothing else.
Oh, okay.
We
Because I think the test is mostly on the convection and radiation portion. They already tested us on conduction, I think.
Okay. I will share you the book and then we will discuss what exactly you need to study now.
Okay. Yeah, I've already done conduction,
Okay.
external force convection, and external force convection on flat plates.
Okay.
So internal pipe flow is on cylinders, is it?
Internal is in
What does
hollow
it fall
cylinder.
under? Again, sorry?
It is a part of hollow cylinder.
Hollow cylinder. Okay. So that means there is force convection on cylinder.
Viscous flow is laminar flow.
Okay.
That is a convection plus conduction combination. There are some formulas which you need to know, like for convection, which is a part of conduction. I will cover that. Then only you will understand. Heat and mass transfer. Okay, so what do we need to study now?
So like the
Understand the basic formulas of conductions for this cylinder, which will be helpful for convection. Okay.
Okay.
Like I will just explain what comes after slab.
Okay, can.
Like this is slab with conduction and convection. Slab is something that is we doesn't have change in cross section with time with length with space. Okay. So next topic would be in the conduction itself, which is also required for your convection. That's why we are taking. Okay. So whenever there will be flow in a cylinder, whenever there will be a flow in a cylinder,
Okay.
the fluid flow will be axial. But the consideration is if the heat flow is radial. Are you getting me?
The fluid flow is what?
Fluid flow will be always axial. Obviously, the fluid will be flowing in the pipe, the way it flows.
Yes, correct. Yeah. But then, okay, I understand. Heat transfer will be.
And that fluid will always have a same temperature throughout. Okay. Then there are two cases. One is called as constant heat flux. You understand the word constant heat flux?
No.
Okay. What is heat flux? Okay. Heat flux is denoted by small q. Okay. Heat flux is denoted by small q, which is simply heat transfer per unit area.
Yeah.
And the unit is watt per meter square. Okay. So when they say constant heat flux is basically nothing but if there is a length of pipe in which fluid is flowing. Okay. If there is a length of pipe in which fluid is flowing,
okay,
the amount of heat at every position leaving would be same.
Okay.
So Q at this point, Q at this point, Q at this point, Q at this point would be same.
Oh, okay. So
that
Q refers to the heat transfer against the area.
No, you can't say against the area. Don't say that. It is per unit area.
Per unit area. Okay.
From a one unit, from a small place, from a unit space.
Okay. And it has to be constant throughout the pipe.
Whenever the word is constant heat flux, it means that heat
okay.
flowing.
So that is constant.
Okay, it's a terminology. Heat flux, constant heat flux.
Okay.
Okay. Firstly, we studied steady flow. In case of steady flow, heat flow rate with time doesn't change.
Yeah.
Now we are talking about heat flow with respect to space.
Okay.
Along the length of the pipe, along the length of the tube.
Okay.
At every position, the heat flow rate is same.
Okay.
Okay, that is constant heat flux. Okay, there are two types of question. One is constant heat flux and another is non-constant heat flux.
Okay.
Okay, that's why I'm covering the topic. We have both the cases in convection.
Okay.
And also in the topic called as heat exchangers.
Can you give me an example of non-constant heat flux?
Okay. Every example, by the way, that we see are non-constant heat flux.
Oh, okay.
Constant heat flux is something that is only for the sake of simplicity.
Oh, okay. So it's like an assumption.
Try to reach the ideal state.
Oh, okay.
Like in thermodynamics, we used to study everything was reversible, ideal. We always do that to find the max value.
Yeah.
Right. So you can say, if what exactly in convection you would be studying. In convection, you would be studying that is there is one pipe inside which one of the fluid is flowing.
Yeah.
Then there will be pipe thickness. That thickness will be throughout its length. Because of this fluid, maybe that fluid is hot fluid, let us say steam. A steam is flowing and that steam will heat the inner periphery.
Okay.
Okay. When the inner periphery will get heated, the heat will flow radially outward. Radially outward. If you see this cross section, it will be like this. The heat will be flowing radially outward at every position.
Okay.
Getting me?
Yeah.
Now this is radial heat flow. Whenever there will be radial heat flow, the formula of heat transfer will change. The basic formula will be same. Q equal to delta T upon R, where delta T would be, if I draw the diagram of this cross section only, the diagram would be like this. A layer of fluid, then there will be a inner periphery of pipe.
Okay.
There will be another outer periphery of pipe. Okay. So the fluid is normally shown or drawn by non-continuous line, or you can say a dashed line.
Okay.
So this is like a fluid. It is just a representation. Okay.
Yeah.
It means that this entire section will be filled with a fluid.
Okay.
It means that fluid will be entirely in this cross section flowing throughout.
Okay.
Okay. So that is just a representation. So this is a pipe. This pipe will have some inner radius R1. Let us give the notation in small letter R1, and outer radius would be R2, small r2. Again, the pipe is made up of some material. It will have some conductivity K.
Okay.
Okay. The pipe will have length L. Okay. There will be some length of pipe.
Yeah.
So there will be heat transfer radially. If there is a heat transfer in radial direction, okay. If the temperatures are written as, if this is temperature T1, if this is temperature T2, and if this is temperature T3, what are these temperatures? T1 is the temperature of the fluid which is flowing inside the pipe.
Yeah.
T2 is the temperature of the inner surface of the pipe.
Okay.
T3 is the temperature of the outer surface of the pipe.
Okay.
Okay. We can complicate this by drawing another layer of fluid at the outside.
No. Okay.
Okay. We can do that because numericals are normal in that form only.
Okay.
But we will not take for the basics. Let us understand how to write the formula. The Q would be same, delta T upon summation R.
Okay.
When you want to draw the electrical analogy of this diagram, of this configuration, you'll have to just focus on any radius throughout. Like let us say I will focus on this radius throughout, from this center to this radius, and then I will not look at the diagram. What I will say is from here to here there is a resistance of convection. Why? Because the fluid is flowing.
Yeah.
Then here the resistance of conduction. That's it. So the temperature over here is T1, temperature over here is T2, and temperature over here is T3. Electrical diagram would be like this: T1, T2, and T3. Here the resistance would be R1 and R2. Okay.
Yeah.
So what would be the heat transfer rate formula? It will be Q equal to delta T upon summation R, which can be written as T1 minus T3 upon R1 plus R2, as it is the one which we studied earlier.
Yeah.
Now R1 is for convection.
Sorry? R1 is
for convection, right?
Yeah, convection.
So formula was
1 over HA.
1 upon HA. Okay. And R2 would be
L over KA.
no. Now the formula would be ln R2 by R1. ln is log to the base E.
Oh.
Okay, ln log to the base E.
Okay.
Log E. That is written as ln.
Okay.
Log to the base E, R2 by R1. R2 is outer radius, is inner radius, upon 2 pi KL.
Okay.
So this is where it differs. Are you still with me?
Yeah, I'm with you. I'm just trying to write this down. I can't find the paper for it. It's okay, I'll write it later. It's fine.
No issues. Okay.
Yeah.
R1 and R2 are two resistances. You can again formulate them like Q can be written as T1 minus T2 upon R1, or can be written as T2 minus T3 upon R2.
R2. Yeah.
Okay, R2. So this was about cylinder. The similar way there is also for sphere. Like had it been a sphere.
Okay.
Okay. For example, I will draw a sphere.
But there's a fluid in a sphere?
Not inside the sphere, but
outside.
Okay.
Okay.
So let us have a sphere.
Okay.
Okay, this is a solid sphere and it has got some core. Okay. And then there is some, you can say a sphere like a ball. A ball has got thickness, right?
Yeah.
Okay, so it's like a ball, a tennis ball.
Mm-hmm.
It has got some thickness. So
Yeah.
you can say this is inside layer and this is the outside layer of the sphere. And
Okay.
we can draw the atmospheric fluid over here. We can draw the atmospheric fluid over here surrounding the sphere.
Okay.
Let us say it is a hot ball just taken outside some vessel.
Mm-hmm.
And it is kept in the atmosphere, and the red color is nothing but the atmospheric air in touch with the ball.
Okay.
Okay. Okay. We will just represent it the way fluids are represented.
Okay. Do you have any tutorials for heat transfer on conduction and convection?
I have all my lectures on YouTube, but those lectures are normally in the combination of English and the regional language. So like I go in Hindi, I go in Marathi, so that everyone can understand.
Yeah, makes sense.
So
Okay, it's okay.
that would be a problematic for you.
Yeah.
Okay. So nomenclatures. This is R1. This is R2. Inner radius of the sphere, outer radius of the sphere. I will just write it down that this is hollow cylinder. So
Okay.
that once you refer the recording, you will be able to understand. This is hollow cylinder.
Mhm.
Okay. And now this is hollow sphere.
Okay.
So the temperature in the inner periphery would be T1, outer periphery would be T2, and this is the fluid with temperature T3. It will have some thermal conductivity K. The fluid will have some coefficient of convection H. Let us say the ball is hot, so heat would flow from inside to outside.
Okay.
The electrical analogy will be drawn for a part of a radius. You can say this. It will look like this: resistance for ball and then resistance of air.
Can I check something? Why is there no resistance for the hollow part of the sphere?
Okay. If suppose they give you some conductivity of the hollow part, then you will consider. If not, then doesn't matter. Okay.
Okay.
That doesn't mean it is scientifically or you can say conceptually affecting it. No. If you see the formulas, we can write the Q either in the form of extreme temperature difference or temperature difference of the individual layers.
So it doesn't affect it.
So even if it is there, if it is affecting the phenomena, it will not mathematically affect the answer.
Okay.
Right?
Yeah.
Obviously, it will have its influence on the heat transfer. And because of that influence, this heat rate will vary.
Yeah.
But without even taking care of that, if you simply take care of these two layers, you will automatically get the correct answer.
Okay.
Right?
Yeah.
Okay. This is T1, this is T2, and this is T3.
Yeah.
It will have resistance R1, it will have resistance R2. Formula is almost same. Heat entering would be equal to heat leaving. Q is equal to delta T upon summation R equal to T1 minus T3 upon R1 plus R2. Okay. R1 is sphere resistance. So here the formula would change.
Okay.
Okay. Here the formula will be different.
Okay.
It will be R2 minus R1 upon 4 pi K R1 R2.
Okay.
Okay. Like these are only three possible formulas you need to.
Okay.
I
don't think we've learned this one though.
What?
I don't think we've learned this sphere.
Okay. There can be only sometimes a specific numerical where you might then have to derive it for.
Oh, okay.
Okay. So instead of deriving it over there, if you remember this formula, then things become easier.
Okay.
Okay, but nevertheless, no harm in knowing it. Okay. R1, then R2 will be 1 upon HA. One small formula, just tell me what would be the formula of A over here?
But the area of the sphere.
No, we're talking about hollow cylinder. What would be the area of the cylinder over here in this formula?
The area of the circle.
What would be the formula?
Oh, pi r square.
No, it is not a cross section area. It is the surface area. Just remember.
Oh, okay.
Okay. So it is cylinder, and cylinder has a surface area of circumference into length.
Oh, okay. So that means if it's, this is for
2 pi R1L.
or even for R1 and R2, is it? Both is 2 pi RL.
Okay. Now this convection was inside the cylinder.
Yeah, so it's the
So the
whole,
radius in contact was R1.
yeah.
So if there had been a convection outside the cylinder,
Oh, then it's okay.
in that case, the area would be 2 pi R2L.
Okay, so then in this case, R2 is just a conduction.
R1 and R2 are the radius inside which the conduction is happening.
No, I mean the big R's, the resistance R's.
Okay, here the small r radius. Okay, right.
Yeah, I mean as in like, okay, so the,
The capital one is for resistance. whereas
yes,
small one is-
capital resistance 1, the area
Okay.
is the surface area of the tube, right?
Yes.
Okay, and then for R2, it's a conduction, correct?
Yes.
Okay, so what's this formula then
This
for
is-
R2?
It is log to the base C R2 by R1 upon 2 by K. It's a mathematical formula derived. There's a derivation for it.
But it's conduction.
For conduction only.
Okay, okay, I get it. Okay.
R2 is for conduction and R1 is for convection.
Convection, okay,
In convection, there will always be surface area.
okay.
Okay, now here the formula has changed because the cross section keeps on increasing.
Okay.
Can you feel the increase in cross section for heat?
Yeah, understand.
Here the radius was R1 and over here the radius was R2.
I think
So every instant the heat is penetrating inside the cylinder. It
that's
is
why the formula is like that.
yes. So it becomes
Okay.
logarithmic function of it.
Okay,
Okay. So these are the formulas for hollow cylinder and hollow sphere.
okay, Ken.
So this is also for conduction only, and this is also for conduction only.
Okay,
For convection, irrespective of the shape of the body, formula is always 1 upon HA,
HA. Okay, Ken.
where A is always surface area in contact.
Okay.
Okay.
You know this thing that you're writing on, is it the Zoom's one?
Yeah, it's a whiteboard on Zoom.
You can't save it, right? The whiteboard.
I can write everything what I can save everything what I'm writing and I can share it.
Great. Can you send it to me?
Yeah, no issue.
Okay, great. Okay, thank you. So we can stop here? Oh,
We can.
yeah. So the next lesson, so how much more we still like how many lessons do you think we need to cover whatever's there?
It all depends on your pace and the content. We can chat it on the topic, like topic wise, we can chat on the WhatsApp. We can discuss like how much time that topic will take.
Okay, Ken. Okay, Ken.
So
Yeah.
I think maybe next time we can cover convection.
Yeah, okay.
Do you have any exams next week or maybe after that?
No, I think it's on August 13. So we still have like three weeks or so. So-
You're working, right?
Yeah.
And what's the schedule?
Okay, I'm free in weekday mornings. And for weekends, maybe at night, like 8 to 10, like this maybe works.
Okay. Weekdays in the morning at what time?
I'm free. Okay, I am free from 9 to 2:30 p.m.
9
or
to
2 p.m.
okay, fine by me.
9 to 2.
Because the time difference is like we are
Yeah,
half hours early, right?
I'm early. You are early, is it? Or I'm early?
We are early.
Oh, okay.
So
then-
here at this time, at this moment, the time over here is 7:40.
Oh, okay.
7:38.
So you can do late classes.
I can take late classes.
So that means like if I want to start like 10 to 12 for my time, it should work for you?
Uh, yeah, it should work. 8 to 10. Okay. No, maybe I'll have my other batches, so it will get difficult for me. We can have morning or
You're
afternoon.
available? Yeah, morning weekdays work for me.
We can plan accordingly. Then weekdays morning.
Okay, fine. Okay.
Like,
So
for me,
the
it will
next
be
one
morning, but for you, it will be mostly near afternoon.
near after like about 11 is okay, right?
11:30.
11:30 works for me.
Okay, 11 because for you when it is 11:30, it will be 9 for me.
Okay.
Okay, so before that, it will get very difficult for me because I have my other schedule.
Oh, okay. So you
Morning
want me
time
to
is basically I avoid working in the morning. So
oh okay. So
it's a workout
how
time.
do you
I
want
work
me
out in the morning.
what's the latest you can start?
We can start at 11:30 or 12 for your time.
Maybe 12 then? 12 to 2?
12 will be fine with me. Okay.
Okay, can. Okay.
Okay.
That works. Okay. Thank you. Thanks.
Okay.
So this the details. I can't do it right now because it's already late. I will send it by maybe next 2 days. Is that okay? The payment?
Fine. No issues. No issues.
Okay. All right. Thank you. Thank you so much.
Thank you. Good
Yeah.
night.
So you can just send me by email the recording and this
Is
right.
it okay if I send you like all the links and this on WhatsApp itself?
Oh yeah, that's fine also.
Okay, fine.
Okay. Thank you. Thanks.
Okay, good
Bye.
night.
Good night. Bye-bye.